Hello, everyone. Thank you for joining us today in this webinar. My name is Eric Wright. I'm going to be presenting the fourth webinar in our webinar series from analog to volumes. I'm going to be talking about how to edit and finalize your map. For 40 years, Petrosys has been an industry leader in mapping and surface modeling software. We will continue to grow and evolve as the oil and gas industry grows and evolves. We service our clients around the world with offices out of North America, Europe, Asia, and Australia. Our portfolio is expanding not only to include exploration software or mapping software, but we're also expanding to include data management solutions. To that end, we have several applications underneath our portfolio. We have Petrosys PRO, a mapping and modeling software that I'm going to be demonstrating today. We have GlobeClaritas, which is a powerful and efficient seismic processing software. We have PLDB, which is our prospect and leads database, which is a subset of dbMap, our master data management solution. We also have Enterica OneView, which is a file archival and metadata analysis tool, which allows you to make intelligent decisions on what projects you'd like to send to cold storage. We have EP Share, which is a document and management solution geared specifically toward the oil and gas industry, built on the SharePoint framework, as well as GP Info, which is a repository of data for the Australian Asian region of the world. Petrosys PRO has been, as I said, continuously evolving as the oil and gas industry has evolved. From 2010 to 2023, we've made great strides in the underlying architecture of our program, as well as the surface modeling and mapping parts of our software. 2024 is going to be a big year for data connectivity. While our data connectivity functionality is very expansive, we plan on improving that and integrating that into our greater software portfolio going forward in 2024. And we're always interested to hear what you'd like to see in our software. So if you have any ideas for improvements or things you'd like to see in the Petrosys software, please feel free to reach out. We're happy to include things in the software. We're not stagnant by any means. Just for a quick recap on where we are on the webinar series. The first webinar was given to by my colleague Jason out of Adelaide, and he was talking about how to georeference a raster TIFF image and bring it into Petrosys PRO mapping. Our second webinar, given by my colleague Abilio out of Perth, talked about how to use Petrosys Spatial Editor and its raster tracking functionality to digitize linear features in that raster image and take them into fault polygons that could be used in your file manipulation inside of Petrosys. The third webinar, given by my colleague Ryan Mooney out of Glasgow, talked about how to take the colorized pixels inside that TIFF image and translate those into Z values for an underlying thickness grid. Which brings us to the fourth webinar, which I'm talking about today, how to finalize that map. I'm going to talk to start off, I'm going to talk a little bit about style templates. What is a map style? A map style consists of the base layout, the map appearance, and the cartographic elements of your map. What I mean by this is map elements are things like your legend, your title block, your north arrow, and so on and so forth. I imagine most people watching this webinar are going to be familiar with many of those elements. Altogether, those map elements are combined into something called a style template in Petrosys. A style template can be regenerated quickly to help you create a presentation quality map. So rather than having to recreate a legend every time you make a map or re-add your title block, all we have to do with the click of a button is click on our style template button inside of Petrosys, and it'll populate your map with these map elements. So you can do that very quickly. It's a great time saver. These style templates can be shared out of something called your local directory. And this is a shared directory that's pointed to by everybody in your company that's using Petrosys. So if I wanted to pass something to my colleague Ashley, I could simply put it in the local directory and she could have access to it, assuming we were on the same network and pointed to the same local directory. I'm also going to talk a little bit today about smoothing. Smoothing can be done in Petrosys locally inside our Spatial Editor tool, and I'll demonstrate that in a bit, or in batch via our surface modeling application. And when I say batch smoothing, I mean we're taking the whole grid and we're applying a single smoothing algorithm across that entire grid. Whereas local smoothing, we're more looking at minute changes within maybe individual contours or individual areas in that greater region. Excuse me. Batch smoothing can occur in the middle of grid passes or after the final grid. and I'll talk to you a little bit about what I mean when I say grid passes in just a moment. But we can either smooth as we're creating the grid or wait till the grid is finished to run all of our smoothing algorithms. Smoothing is something I would consider ideal for maybe badly tied seismic data, not so much for data where you have great control, such as well data, or data without significant misties. Usually I would recommend one smoothing pass, regardless of what type of data you're working with, just to clean it up a little bit. But if there is good controls, then you probably don't need heavy smoothing in that map. Other ways to smooth outside of batch smoothing and localized smoothing can include regridding or resampling the grid to a coarser cell size. Smoothing will discount any changes that are smaller than one cell size. So if you're working with a cell size that's maybe too small for the region you're working with, you won't see a great effect from the smoothing. So oftentimes what you will do is resample the grid to a larger cell size and then run your smoothing algorithm to get the best effect. And I'll show you that in a bit when I demonstrate the software. I'm also going to talk a little bit about embedded faults. What is an embedded fault? An embedded fault is when we take a fault polygon either from Petrosys or a third-party software and combine it with other input data to create one Petrosys grid file. So that way you don't have, rather than having a fault file or a fault polygon from Petrel and a grid file from Petrosys, you just have one grid file from Petrosys. It is combined in that grid file. That is an embedded fault. Faults can come from a great number of third-party sources, not only Petrel, but we can also accept fault data from Arc, Dug Insight, Kingdom, OpenWorks, Sizeware. We can also incorporate faults from shapefiles. Data connectivity is something that's very strong in the Petrosys software. And this is also true when you're working with embedded faults inside the Petrosys environment. Faults may contain z-values, which are used as gridding inputs. What that means is that when you're working with, say, a structural grid or a thickness grid, we can actually record z-values alongside those faults, and these faults will be used to influence the gridding process. Maybe incorporated into any immediate gridding passes, and I'm going to explain that in just a second. What do I mean when I say intermediate gridding passes? To understand what I mean by that, we're going to have to take a look at how Petrosys creates a grid. The first step when Petrosys creates a grid, it analyzes your area of interest. This is either your map extent, which is what Petrosys calls an area of interest, or your underlying grid geometry. It analyzes that. We then take the input data points, such as your well data or other seismic data you might have, and we analyze that and get it ready for use in the gridding program. Then takes the cell size that you put in, say for example 200 by 200 in this case, and then what it does is it goes through a doubling process. It continues doubling that cell size until it gets to an area that is at less than or equal to 8 by 8 in cell size. Once it hits this coarse grid, so to speak, it then starts to halve it again. But as it halves it, it starts recording values at each of the grid nodes, right? So we start with a really coarse grid, that's grid pass 1, and we record values at each of these grid nodes. As we have it in successive passes, we record grid values at those grid nodes again. This would be pass 2, for instance, the first halving event is pass 2. And so on and so forth. As we continue having, we keep recording values at each of these grid nodes. And that's how Petrosys creates a grid until we get that, and it keeps having it until you get to your original input grid cell size, and then it interpolates it with a color fill. And the reason why that's important is because faulting can be included in any one of those grid passes, and I'll show you what I mean by that in the next slide here. Again, talking about going back to a little bit more detail about how we embed faults. Many third-party data types are accepted. The z-values of the embedded faults will influence your gridding. Faults may also be used as boundary polygons. And what this means is that it's true to its name. If you want to use the faults as a boundary polygon, you can do so. This is important in areas that you may have different oil-water contacts and different fault blocks. That's an example of a time you'd want to use this. We can also grid inside faults. When you set this option on, this is important for volumetrics. If you don't grid inside faults, your volumetrics will not pick up data inside that fault polygon. Therefore, you won't have accurate volumetrics. So if you're working with volumetrics, it's accurate. It's important to have this option checked on. The number of passes to use faults is how we specify when in the gridding process we begin including those faults. Again, as the grid cells in the grid creation process are halved, this option will allow you to specify when you'd like to start looking for fault data, basically. The input data clipping distance will also allow you to clip your data to minimize any anomalies around faults. Say, for example, if you have bullseyes or areas where you think that you don't want to account for maybe fault shear or thicker areas, you may want to use this clipping data. You may want to clip the data around those faults to eliminate those anomalies. Similar to fault polygons, we can also work with fault sticks. Fault sticks, just like with fault polygons, can be taken from a number of third-party data sources, primarily Petrel, OpenWorks, Kingdom. There's not as many third-party data sources that we accept fault sticks from, but most of the main third-party exploration packages we can. Again, just like with fault polygons, gridding inside fault polygon the fault polygons that are created from your fault sticks is going to be important for volumetrics. The model fault plane between sticks is going to be suggested when your fault sticks are primarily horizontal. So if you have a lot of horizontal fault sticks, you may want to have that option turned on. What it does is it generates an array of vertical fault sticks in your fault stick selection and uses those to create fault polygons from that. Searching for context in every gridding pass, this is a comparative option. It'll make some of your areas where you have fault sticks maybe look better, and it might make some areas look less better, less good, depending on if you have checked it on, depending on if you have it checked on or off. It'll enhance certain areas, and if it's checked on, it enhances other areas. If you have it checked off, you may want to try both. It's just what it does is it specifies what gridding pass you'd like to start looking for fault sticks. The input data clipping distance is the same as in fault polygons. When you're working, you have the option here to clip data when you're working with fault sticks as well. Minimum heave allows you to set a minimum heave for your fault polygons. So in other words, this is when you have really vertical fault sticks that may not have a lot of heave. This will look like really skinny faults when you're working on it in a mapping environment. The minimum heave will allow it to have a little bit thicker of a shape on your map so that it's not so skinny, so to speak. That said, I'm going to go ahead and start the demonstration. So let me go ahead and move this aside. Bring this over here. And here we are. This is the Petrosys PRO mapping environment. What we're looking at is a GeoTIFF that's been geo-referenced previously in the first webinar and brought into the Petrosys PRO mapping environment. The red faults were digitized with the Spatial Editor raster tracker, and these are linear features that are in a Petrosys fault file. The underlying grid that was created from this raster is currently being shown in black contours here. I have the color fill turned off. You're just looking at the black contours. And the first thing I want to do is take a visual QC of the grid that we've created from this raster. We're going to talk a little bit about smoothing, localized smoothing, how you might get rid of some of these black blobs. And then I'm going to go ahead and do a comparison when we run batch smoothing, when we run this grid through batch smoothing, so you can see the effects of different smoothing passes and how that might affect this surface. So the first thing you want to notice is that if you're looking at this grid, you may see some black blobs kind of in these regions on the map over here. What I'm going to do is I'm going to zoom into a couple of those. Let me see. And to zoom in, I'm going to change my area of interest by going here to the bottom right and selecting extent. And again, extent in Petrosys is just another word for area of interest. And I'm going to click on this one that says fixing contours so I can zoom in just a little bit. And that's going to give me a map. I'm going to pull up this little map. I'm going to cancel out this real quick. And to prevent loading times, what I'm doing is I'm substituting maps in and out, sliding maps in and out so that saves a little bit of time on loading. I'm going to zoom into this area right here, this region on the map, so you can see an area that looks very wonky, so to speak, with its contours. This happens a lot when you're working with image data. You're working with colorized pixels. The input data isn't exactly perfect, and subtle changes in those colorized pixels Say, for example, if you're working with a really flat area, will be picked up by the raster grid program, and it will create these little artifacts in here. And this is something that happens just when you're working with image data. What we're going to do is we're going to eliminate this little blob here by taking this into Spatial Editor. And again, Spatial Editor is our tool that we use to make localized changes to our map. I'm going to right-click on this grid that's being shown here. I'm going to select Edit, and this will load it into that Spatial Editor. Okay, now that the contours have been brought into Spatial Editor, what I'm going to do is show you how to run some localized smoothing as well as edit the grid nodes that are making up this region on the map. I'm going to turn up the color fill to make it a little less noisy visually. The first thing I want to show you is how to edit a contour locally using our local smoothing. And to do that, we're going to go here in Spatial Editor, which is this left hand, which is when I say Spatial Editor, I'm referring to this left toolbox on the that has all my edit buttons. I'm going to flip this drop-down box to contours, and that's going to allow me to start editing some of these contours in this region. To edit a contour, I'm going to click on it, left-click on it so that it turns it red. Once this contour has been highlighted in red, Spatial Editor has recognized that this is the contour I'm targeting for edit. To do localized smoothing, I'm going to select Smooth Kinks from Selected Shapes here. It's the fourth option on the third row inside of Spatial Editor. I'm going to left click once so that my mouse has now become a circular cursor. I'm going to hold down the left click button, and as I do that, you're going to see my contour slowly get to be smoothed out. All I'm doing is left clicking, I'm holding down and going over this area that may have a few kinks. I'm just trying to illustrate how the localized smoothing might work when you do it yourself. This is just to smooth out one particular area of my grid, and I can even smooth out maybe this contour a little bit. I tend to use this a lot when there's seismic data. Okay. Anytime you edit contours inside of Petrosys, you need to regrid them locally. What local regridding is, it regrids a section of the grid that you made changes to while leaving the rest of your grid intact. To do local regridding and saving your contour changes, you go up here to gridding and you select regrid changed areas. And you can see here that the Spatial Editor has picked up the areas I've changed and highlighted in pink. It recognizes that the only area of this grid I want to change is here in pink. It's not going to touch the rest of it. I've already have a grid prepared, so I'm not going to run the regridding process on this right now. Plus, I want to show you how to get rid of this blob here. So I'm going to cancel out of this. I just wanted to show you where you would go to do the local regridding functionality if you wanted to. So if I cancel out of that, with the assuming that the local grid would have happened, what we're going to do now is clear out this blob. And what this blob is, each one of these contours is actually a 4,000 foot contour. If you can see here at the bottom of my screen, you can see each one of these is 4,000 feet. This is a thickness grid, so it's 4,000 feet of thickness. What we're going to do is edit the underlying grid nodes to read 4,000. And to do that, I'm going to go here to this drop-down box, and I'm going to select grid nodes. I'm going to hit OK. It's just asking me, are you sure you want to do this? And when you're working on this on your own, I highly recommend saving out to a different file first in case you make any mistakes. It makes it easy to go back and undo any mistakes you may have made when you're working with the grid. As long as you don't save anything, you're not going to save over your data, but I always recommend making a new file anytime you work in Spatial Editor, just so you don't make any accidents. All right. So now I'm in the grid node editor rather than the contour editor. And what this is, I'm going to turn on the contours here because they seem to disappear. There they are. And what I'm going to do is I'm going to edit every grid node in this region and set it to 4,000 to get rid of this little black blob here. To do that, I'm going to use the fifth tool on the fifth line here in Spatial Editor, adjust grid values inside and outside polygons. And this is just another way you can smooth and or edit data inside of Petrosys. I'm setting the mode to set value because I want to set the value to 4,000. Petrosys remembers that the last time I did this, I also was working with the same contour set. I'm going to type in 4,000 Going to adjust the values inside of polygons. And what I'm going to do is I'm going to hand pick an AOI, hand pick a polygon around this because I'm just picking this little area. And what it's doing again after I finish digitizing this polygon is it's going to set every grid node here to 4,000. And if you make a mistake, you can just right click once on your mouse and it'll undo the last pick you've done. All I'm doing is just left clicking around, nice and easy. Again, we're working with raster data. This isn't very this isn't very maybe accurate data. It's coming from a picture. It's not coming from like well data or anything like that. So I feel very comfortable about just making this region and setting it to 4,000. Once you've adjusted once you have your polygon picked, you just hit apply. And once it's done, you can go ahead and close. And these are just visual artifacts that are in here from the spatial editor. They will go away when you actually create the grid. And then to save your grid, you'll click on your little color fill and you'll go to File and Save. But since I don't want to save over my save this, I'm going to go ahead and just show you a different map. I'm going to slide over a different map, show you what it might look like after you've done those spatial editor edits. If you look here, this little region where that black blob was originally is no longer there because I used the spatial editor method that just shown to take out that little black blob. And this is kind of what it looks like after you regrid it. You can see I've also cleared out another area up here that's top right as soon as it loads. Yeah. All right. Yeah, you can see I've cleaned up certain areas on this grid, like this black blob that was originally here on the right-hand side is no longer there. That was all done using Spatial Editor. Next thing, if we want to go back, I want to talk a little bit about batch smoothing. And again, batch smoothing is when we take this whole grid and send that into our surface modeling, which I will show you in a bit. Let me get the original grid out and slide that over. Original grid looks something like this. Let me turn up the raster. So you can see just the underlying contours. And this is before I made Spatial Editor edits. So that's one way we can edit a grid locally using Spatial Editor. The second way, again, is we're going to do batch smoothing. And when I first started doing this, I first originally hit it with just a simple, I hit it with a simple Bartlett 7 first. I didn't do any other smoothing algorithms. The Bartlett 7 is our hardest smoothing algorithm that we have inside of Petrosys. It's a very complex one. And after running it through this 100 by 100 meter regional grid, you can see that the Bartlett 7 didn't actually make many changes to the original contour set. Now, why is that? Why is the hardest smoothing algorithm that we have inside of Petrosys not changing this at all? Well, that's because the underlying grid cell size here within this grid is too small for the changes to be picked up by the smoothing algorithm. Again, smoothing is going to discount anything that is larger than one grid cell size. So to enhance the smoothing, what I did then is I resampled this grid to 2,500 by 2,500 meters, and then ran a different smoothing algorithm on it. And I'll show you what that looks like right here. Bring this over, and you can see here after resampling the grid to 2,500 by 2,500, and then running a biharmonic smoothing algorithm, you can see the changes from smoothing take effect a little bit better. Biharmonic smoothing, opposite of Bartlett smoothing, is it's probably our easiest or less harsh smoothing algorithm that you can use inside of Petrosys. But after resampling, you can see the effects that this biharmonic algorithm has had on this grid surface. You can see it's actually made significant changes to the contours, including areas like this little black blob that we took out in Spatial Editor using local smoothing. You can see how it's really smoothed out some of these areas here quite significantly. And this is because of the resampling effect. Anytime you're working with large regional data sets, I strongly recommend you resample your grid before you run any kind of smoothing algorithm. You can think of it as like an enhancement to your smoothing algorithm, if you will. I'm going to show you how this is created inside of surface modeling. But before I go ahead and do that, I'm going to show you how to turn on map elements and turn on the map style here in Petrosys. You may notice there that my map is looking a little blank. There's no coordinate system, there's no north arrow or anything like that. To recall that data, to recall those map elements, I'm going to go down here to the bottom right. I'm going to select the style the style option right here, where it currently says nothing, and I'm going to select the interpret and refine style that I've created for this webinar. Before I click OK, I want you to notice this location column. There are 3 places that a style template can be saved. There's the system location, and this is what we call inside Petrus for just your installation files. So for example, these come default when you install the Petrosys PRO software suite. There's the site location, and this is another name for the local directory. This is where if you want to share something among colleagues, you'd want to save it to the site. There's also the project location, which means it's saved local to this project. That means no one else in the company is going to be able to see this template unless they're working inside of this project. So I'm going to go ahead and hit OK. And once I do that, you're going to see my map elements get populated here. And there you go. With one click of the button, Petrosys has added map elements to my my work. I didn't need to take any time at all. It saves me a lot of time rather than having to sit here and individually turn on my color bar, my north arrow, my location map, and so on and so forth. It's a huge time saver just to be able to recall those map styles. And again, if I want to pass this map style to my colleague Ashley, I could do that by saving it to my local directory, and she could use it as well if she wanted to, as could anyone who's pointed to that same local directory. I imagine most of you are probably going to be pretty familiar with most of these map elements, so I'm not going to go into too much detail of what they actually are, but I will show you exactly how to display them. To display a single map element, you go here to Display, and then you select Map Elements here, and you can see the different types of map elements you can display. Most of them are probably pretty self-explanatory. The location map in general is very interesting because you can actually use another Petrosys map if you wanted to use it as a location map. The legend itself will auto update. If I go ahead and map, I'll just go ahead and select map elements and legend. The map legend itself automatically recognizes any well data or GIS data, and it populates and creates a legend for you, so you don't have to individually go through and add each one of those items to your legend. However, if you do wish to do that, and if you wish to create legend items for other things, such as seismic data or other individual items, you can do that by clicking the Add button here at the bottom left. You can also import other items using the Import button. You have a lot of great control over how to design this legend and make it to your liking. I'm going to cancel out of that. Just a little brief show on that. The title block I'm showing here is actually coming from an Excel spreadsheet. To give you an idea what that might look like, it's actually pretty easy for anyone to create. The title block in Excel is simply a section of Excel cells with the Petrosys logo, as well as some runtime text substitutions here. So these will accept inputs from the user inside the Petrosys environment, as well as populate items automatically in the title block here. For my map, such as the map scale, the date, the units that the map is saved in, all those are auto-generated from these runtime text substitutions that are found here inside the Excel spreadsheet. So that's why you can populate map elements very quickly on your map. What I'm going to show you now is surface modeling. I want to talk a little bit about how we may embed faults and how we run these batch smoothing processes inside of surface modeling. So I'm going to slide this to the side here for a moment. 1 second. Minimize all these. Excuse me for 1 second. I'll get my surface modeling out. So surface modeling is going to be one part of our application. When you start the Petrosys PRO application, it's going to be a component found here on this surface modeling button. When you first start surface modeling, you're going to have a blank task that looks like this. To do embedded faults or grid smoothing, you're going to go to Grid and Create Grid. And this is where we do most of, I would say, a lot of our, this is where a lot of tasks are going to start. Creating your first grid. You're going to have columns for input data. You'll see here there's tabs here for input data, output geometry, methods, faults, and smoothing, and clipping as well. If we click on the one for faults, this is how we get to the dialog and to add faults to our grid. You would want to browse your fault selection and incorporate faults inside your grid by clicking on this little drop-down box here and selecting the fault file. And again, if you have faults coming from Petrel or OpenWorks or any other third-party data source, we can also incorporate that into our Petrosys grid as well. This is how embedded faults works. You have your options down here as well, just like as discussed before in the PowerPoint. Your smoothing options are going to be here. If I click on smoothing, you have, again, controls on when you want to start your smoothing. Do you want to smooth as the grid is being created, or do you prefer to run smoothing passes after the grid is created? That's what this option is going over. If you want to control more smoothing after gridding, you also have more powerful operators here, such as the biharmonic, which is the lightest form of smoothing, and the Bartlett 7, which is the harshest form of smoothing. These algorithms are roughly listed from lightest form of smoothing to heaviest form of smoothing. If you're running smoothing, I'm going to cancel all this real quick, and you're running your task, you can actually become pretty arduous. I'm going to show you what the task list I was using when I was working for this webinar. For one grid, I was doing a bunch of comparison for different smoothing algorithms, and you can see here the task list becomes quite expansive. This is just, again, for just one grid. Luckily, Petrosys surface modeling is a very powerful tool in that if you wanted to run this same task list over a directory of grids, for example, we can automate that using some very simple scripting commands so that I can run this same list of smoothing operations across a directory of grids if I wanted to, with just the one click of that button. It's a repeatable and iterative process, and it allows me to compare a lot of smoothing algorithms very quickly and create these smooth grids very quickly with little time on my part as a exploration geologist. So it's a huge time saver using this tool and having it loop over this like a directory of grids rather than going through each grid one by one and having to rebuild this every time, because that would be quite arduous. If anyone out there is interested in building one of these workflows or learning how to build one of these workflows, please feel free to contact me or anyone else in Petrosys support, and we'll be happy to help you construct one of these workflows to smooth your grids and make it repeatable so that it goes through your entire working directory. The final step here is that actually I've written out, I have a draw map function inside my workflow, which will update all my maps with my new smooth grids. So that way, if every time I run this workflow, my maps will be updated as well. So I can do this for hundreds of maps if I wanted to. I could update each grid for hundreds of maps, and I could do this very easily. But I appreciate everyone coming here and listening to the webinar. Our recording will be up on our website, on our YouTube website. If you want to follow us, you can also follow us on LinkedIn. Again, if you have any questions, please feel free to email me, eric.wright@petrosys-usa.com, or contact us at info@petrosys.com.au, and we'll be happy to answer any questions you may have. Thank you very much, everyone, for your time.